Once again, I welcome in the course Introduction to Fluid Mechanics. So in the last class, I have discussed about the what is the difference between Newtonian and non-Newtonian fluid, and then we have seen the various types of non-Newtonian fluids, and we have also discussed the various example of non-Newtonian fluid. So today I will discuss the problems based on the Newtonian and non-Newtonian fluid, and then I will discuss the concept of surface tension, and then I will discuss the application of surface tension, and then I will take problems based on this. So let us start the first problem. Classify the substances for which velocity gradient and shear stress variation are given below. So the value of velocity gradient in radian per second, that is 0, 1, 2, 3, 4, and corresponding shear stress is 2, 3, 4, 5, 6 kilopascal. In the second part, we have to find for this, we have to classify the fluid for this variation, and in the third part, we have to identify the fluids for this shear stress and velocity gradient variation. So let us take the first one is the velocity gradient du by dy in radian per second. If I talk about the first, and the shear stress in kilopascal is given, and it is 0, 1, 2, 3, 4. So 0, 1, 2, 3, and 4. So the velocity gradient is 0 radian per second, 1 radian per second, 2 radian per second, 3 radian, and 4 radian per second. And if I see the shear stress, so shear stress is given corresponding to this velocity gradient is 2, 3, 4, 5, 6. 2, 3, 2, 3, 4, 5, 6. So here we can see that when the velocity gradient is 0 means there is a shear stress. This shear stress is called initial yield stress or initial shear stress. Means we have the this is the types of non-Newtonian fluid, because initial yield stress is there. So if there is some initial interest, so either it will be ideal plastic or thixotropic or rheopectic. So we have to check. So according to we know that tau is equal to A du by dy to the power n plus b, where tau is the shear stress, A is the apparent viscosity, n is the constant, and b is initial yield stress. So if I write d tau by d du by dy, so it will be A into n du by dy to the power n minus 1, and b is constant, so it will be 0. So if I see the slope of tau du by dy curve is, what is the slope of tau versus du by dy curve is a n into du by dy to the power n minus 1. So this slope will increases if du by d increases and the value of n is greater than 1, and it will decreases when n is less than 1. So we can write the slope of increases with du by dy if n is greater than 1. Similarly, we can write if n is less than 1, so the value will be and decreases if n is less than 1. If n is equal to 1, so the slope will be, here we can see that when n is equal to 1, so it will be slope will be constant. So if n is equal to 1, so the slope will be constant. So here we can see that if I compute the d tau by du by dy, so d tau by du by dy, if I compute, this is du by dy radian per second shear stress, and d tau by d into du by dy. So the shear stress is given 0, 1, 2, 3, 4. So 0, 1, 2, 3 and 4. And similarly the value of shear stress is 0, 2, 4, 6. 0 to, so it is 0, 1, 2, 3, 4, and the shear stress is 2, 3, 4, 5, 6. 2, 3 here. This value is 2. This value is 2, 3, 4, 5, 6. So if I compute the value of d tau by du by dy, if I compute the value of d tau by du by dy, so for this value it will be d tau means 3 minus 2 divided by 1 minus 0. So it will be 1 by 1, 1. Similarly for this fluid, so it will be d tau is 4 minus 3 divided by 2 minus 1. So 4 minus 2, it is 1 by 1, so it will be 1. Similarly for this, so it will be 3 minus 2 divided by 5 minus 4, so it will be 1. And for this 4 minus 3, 1. 4 minus 3 divided by, sorry, d tau 6 minus 5 divided by 6 minus 5 divided by 4 minus 3, so it is also. So here the slope is constant. So here we can see that d tau by d du by dy is constant. So we can write slope is constant. So when slope will be constant, either in case of Newtonian fluid or in case of uh, uh, in Newtonian fluid and in the non-Newtonian fluid, where the fluid is ideal plastic or Bingham plastic. So this is because uh, here the initial yield stress is 0 when du by dy is 0. When du by dy is 0, so the shear stress is how much? 2 kilopascal. Shear stress is 2 kilopascal. So this is the example if I draw. So this is shear stress and this is du by dy. So this will be the, this value is 2 kilopascal. This is ideal plastic or Bingham plastic. So fluid is non-Newtonian. So fluid is non-Newtonian and it is Bingham plastic. Let us take the second problem. The shear stress is given. So in the second part, du by dy shear stress d tau by d dy by so if I take the value, so it will be 0, 0.3, 0.6, 0.9 and 1.2. 0, 0, 0.3, 0.6, 0.9 and 1.2, and the shear stress is 0.2468. So 0.2468. So if I compute the value of d d sigma by dy, so this value will be d tau. So 2 minus 0 divided by 0.3 minus 0. So it will be 2 by 0.3. So 2 by 0.3, 2 divided by 0.3. So it is 6.67. 6.67. Similarly here, so 4 minus 2 divided by 0.6 minus 0.3. So it will be once again 6.67. Here 0.9 minus 6 minus 4 divided by 0.9 minus 0.6. So it is 6.67. And here 1.2 is 8 minus 6 divided by 1.2 minus 0.9. So 6.67. Once again slope is constant here. So we can write here slope is constant. So slope is constant. So once again either the fluid can be Newtonian or non-Newtonian. If the Newtonian, so it will be we can see here whether intercept is there or not. So when du by dy is 0, so shear stress is also 0. Means it is the case of Newtonian fluid. Newtonian fluid, because if I draw the tau versus du by dy, so this is tau and this is velocity gradient and no intercept or no initial yield stress. So this is the uh, Newtonian fluid. In the third part, so third part, if I compute, so this is du by dy shear stress and d tau by d into du by dy. So if I see the question, so it will be 0, 0.5, 1.1 and 1.8. 0, 0, 0.5, 1.1 and 1.8. And the shear stress is 0.246. 0.246. So if I compute the slope, so slope will be 2 minus 0 divided by 0.5 minus 0. So 2 by 0.5 means it is 4. Here 4 minus 2 divided by 1.1 minus 0.5. So it will be 2 by 0.6. 2 divided by 0.6. So it is 3.33. 3.33. Similarly here 6 minus 4 divided by 1.8 minus 1.1. So 2 by 2 divided by 0.7. So here 2.85. 2.85. So here slope is not constant. Slope is not constant, and slope is once the du by dy is increasing, so the slope is decreases. Here we can write slope is decreases with increase in du by dy, and when du by dy is 0, so shear stress is also 0. So this is the example of, this is shear stress, and du by dy, intercept or initial yield stress is 0 and slope is decreases. Slope is decreases. So this is the example of pseudoplastic. Pseudoplastic. When du by dy is increases, so slope will decreases. So it is the example of pseudoplastic. Let us take the another problem. So if I talk about this second problem, so which of the curve labeled as 1, 2, 3, 4, 5, 6 in the given figure represents the Newtonian elastic solid and ideal fluid respectively? Six curves are given: 1, 2, 3, 4, 5, 6. This is fifth one and this is the sixth one. So this question is asked in civil services exam, and the options are 1, 5, 6, 2, 4, 5, 3, 4, 5 and 4, 6, 5. So if I draw the, so this is the shear stress and velocity gradient. This is the Newtonian fluid. This is the dilatant. This one is the pseudoplastic. This is the ideal plastic. This is the thixotropic, and this is the rheopectic. Initial yield stress B is here, and this fluid is ideal fluid. This is ideal fluid, and on this portion, this is the elastic solid. Elastic solid. This is dilatant Newtonian fluid. This pseudoplastic, ideal plastic. This is thixotropic, and this is rheopectic. So if I see the option, so options are Newtonian, elastic solid and ideal fluid. So Newtonian, so it will be 4, 6 and 5. So D option is correct. Let us take the another problem. So the velocity distribution over a flat plate is given by u is equal to 3 by 4y minus y square, where u is the velocity in meter per second at a distance y in meter above the plate, and mu for the fluid is 0.84 Newton second per meter square. The shear stress at a location 0.3 meter above the plate is k times the shear stress at location 0.2 meter above the plate. The value of k would be. So once again, this question is asked in civil services examination. Velocity distribution is 3 by 4y minus y square, and the shear stress dynamic viscosity is given 0.84 Newton second per meter square, and the condition is given the shear stress at a location 0.3 is equal to meter is equal to k times the shear stress at a location of 0.2 meter above the plate. So here we have to apply the Newton's law of viscosity. So according to Newton's law of viscosity, tau is equal to mu du by dy. So if I write tau 0.3 is equal to mu into du by dy, or we can write mu into du by dy. So it will be 3 by 4 minus 2y. 3 by 4 minus 2y at y is equal to 0.3 meter. Similarly, tau 0.2 meter is equal to mu 3 by 4 minus 2y at y is equal to 0.2 meter. So the value of k will be tau 0.3 by tau 0.2 meter. So the k is equal to tau 0.3 meter divided by shear stress as 0.2 meter. So the shear stress will be at 0.3 divided by shear stress as 0.2 meter. So dynamic viscosity will be cancelled. So the value of k is equal to 3 by 4 minus 2.2 into 0.3. So it is 0.15 divided by 0.75 minus 0.4. So it will be 0.35. So the value will be 3 by 7. So if I see the option, so it will be C option is correct, 3 by 7. Question number 4. Which of the following fluids can be classified as non-Newtonian fluid? The first one is kerosene oil, diesel oil, human blood, toothpaste and water. So here I told you in the previous lecture that the water, air and kerosene oil, diesel oil are the example of Newtonian fluids. So this kerosene oil, diesel oil and water are the example of Newtonian fluid. Human blood and toothpaste are the example of non-Newtonian fluid. So option is B, 3 and 4. So here we can see that I have written the example of different fluids. If I talk about the example of Newtonian fluid, so it is water, air, gasoline, and property I have written when n is equal to 1 and initial yield stress is 0. Similarly, the example of dilatant is solution with suspended sand, starch, and butter. And the value of exponent n is greater than 1 and b is equal to 0. Similarly, the pseudoplastic n is less than 1 and b is equal to 0 because this is the concavity downward curve. So the value of n will be less than unity. And the examples of the pseudoplastic is paint, blood, paper, pulp. Similarly, the example of thixotropic is printer's ink, and the example of ideal plastic is toothpaste, drilling mud. So I have written the example of different fluids. So now I am going to start the surface tension, new concept, that is surface tension. So surface tension, the basic reason of this surface tension is the cohesion or cohesive force, and it is the property of surface or liquid interface. So let us take the example of the surface tension. So very simple example, if you put the water in a bucket, so at the top, at the surface, we can say that the different water molecules are present. And let us example, this is the this is the surface, this is the surface, and different water molecules are present at there. And below this also water molecules are there. Here is also water molecules. So here between two water molecules there is a cohesive force will act, this cohesive force, and the net force at this portion will not be equal to 0 because in atmosphere or air it will not be balanced. So the net force in the water molecule, net force in the water molecule is not equal to 0. And what will happen, this cohesive force, entire cohesive force will act downward. So the net cohesive force net cohesive force will act downward. So if I talk about the very adjacent to the this surface, so what will happen, this top water molecules will be in tension, because entire water molecules will try to move downward, but due to these molecules will be in tension, or tensile force will act at these molecules. So if I see, this is the scenario, this is tension and this is also in tension. If net downward force, net cohesive force, that will act in downward. So if I write, the entire molecules, water molecule will act downward. So to maintain equilibrium, the tensile force will act, or tension force will act at the surface, and that this phenomena is called surface tension. So surface tension is also defined as surface tension is also defined as force per unit length. It is also defined as work done per unit specific surface area. So if I write here the surface tension, so it is denoted by sigma. It is denoted by it is denoted by sigma, and unit is Newton per meter. So at the interface, if I write the total tension force Fs is directly proportional to length of interface. So we can write Fs is directly proportional to the L. So here Fs is the tension force. So this Fs, if I remove the constant of proportionality, so it will be sigma into L. So here sigma can be written as Fs divided by L. So that's why I have told you that surface tension is the force per unit length, or tensile force, tension force is sigma into L, where sigma is the surface tension. Surface tension. So there are three applications of this surface tension. So if I talk about the application of surface tension, application of surface tension. So there are three applications of surface tension. The first one is pressure in the water droplet. Water droplet. Second one is pressure in the soap bubble, and the third one is pressure in liquid jet. So let us discuss one by one. The first one is pressure in the water droplet. Pressure in the water droplet. Let us assume this is the water droplet, and the shape of this water droplet is spherical. Why? Because I told you that the surface tension is the work done divided by specific surface area, and we know that the specific surface area is minimum for the spherical shape. So once it will act on the any surface, so it will try to stable. So the shape will be the spherical. That's why the shape will be spherical, because specific surface area should be a minimum. So the specific energy should also be minimum. So if I cut, that's why I have here I have taken the droplet is shape of this shape. Let us assume this is the water droplet. This is the water and the air. So if I cut it along this, inside pressure is Pi and outside pressure is P naught. So if I see the one portion, let us assume this portion will look like, so this portion will be look like this. So what will happen in this surface? The bursting force will act, and opposite to this resisting force will act. So this is the bursting force, or also called pressure force, and here is the resisting force or surface tension force will act. So to maintain equilibrium, this bursting force will be equal to the resisting force. So what will be the bursting force? Bursting force or pressure force. So what will be the pressure force? So if the change in pressure, that is Pi minus P naught, is delta P. So let delta P is the change in pressure. So delta P into area. So area will be pi by 4 into d square, because this d is the diameter of this water droplet. Here delta P is equal to Pi minus P naught. Pressure inside minus pressure outside, and d is the diameter of the water droplet. Here dp is Pi minus P naught. Pi is the inside pressure and P0 is the outside pressure. And one thing, inside pressure is always greater than outside pressure. And d is the diameter of water droplet. So the bursting force or pressure force here is equal to delta P into pi by 4 into d square. Similarly, the resisting force or surface tension force, resisting force or surface tension force is equal to how much? So if sigma is the surface tension, so sigma into pi into d. So sigma into pi into d. So for equilibrium, this bursting force must be equal to the resisting force. So for equilibrium, bursting force must be equal to resisting force. So what is the bursting force? That is equal to delta P into pi by 4 into d square is equal to sigma into pi into d. So pi cancel, dd cancel. So delta p is equal to, it will be 4 sigma divided by d. So delta p is equal to 4 sigma divided by d. So in case of water droplet, change in pressure, in case of water droplet change in pressure is equal to 4 sigma by d, where d is the diameter of water droplet. Let us take the another application, that is the pressure in soap bubble. Second application, pressure in soap bubble. So the best example of soap bubble, when you put the detergent in the bucket, so there is a formation of bubble, that is the soap bubble. So once again, if the shape of bubble is this one, so if I cut it once again, and inside pressure is Pi and outside pressure is P naught. But one thing here, you remember that this is also air and this is outside is also air. So once again, if I see the this portion, so it will look like, so once again the bursting force will act and the resisting force will act in this direction. So this is the bursting force, and here is the resisting force. But one thing here is change the surface tension, because inside there is a inside bubble there is air, and outside there is also air. So the surface tension will act twice. So here bursting force we can write that is equal to delta P into pi by 4 into d square, and the resisting force will be sigma into pi into d into 2 times. So it will be sigma into pi into d into 2. Once again, if I equate this bursting force and resisting force, so bursting force is equal to resisting force. So bursting force is delta P into pi by 4 d square is equal to sigma into pi into d into 2. So here delta P is equal to 8 sigma divided by d. So in case of soap bubble, the change in pressure is 8 times the sigma by d. In case of water droplet, we have seen that the delta P is equal to 4 sigma by d. Here delta P is equal to Pi minus P naught. Sigma is the surface tension and d is the diameter of soap bubble. Similarly, the next case that is I am going to discuss, that is pressure in the liquid jet. So pressure in the liquid jet. Third application, pressure in liquid jet. So let us see, this is the nozzle, and this is the diameter d. This is nozzle, sorry, liquid jet. This is nozzle. So if I cut this portion, so it will look like a cylindrical shape. So a liquid jet of length, let us assume the length is L and diameter is d. So it will look like a cylindrical shape having diameter d and length L. So if I cut it by this way, so it will look like will look like that. This is diameter and this is length. So if you see the bursting force will act in this direction and the resisting force will act in this direction. If I cut it, so bursting force will act in this direction. So bursting force and this is the resisting force. So here bursting force, if I write, so the bursting force is bursting force is equal to delta P into L into D, and the resisting force is sigma into, here we can see that sigma into L plus L, so 2L plus 2D. So we can write sigma into 2L plus 2D. But here we can see that the length is much greater than diameter. So in liquid jet, length is much greater than diameter. So resisting force or surface tension force can also be written as sigma into 2L. So if I equate this resisting force, so sigma into 2L is equal to delta P into L into D. So here delta P is equal to LL cancel, so it will be 2 sigma divided by D. So this is the change in pressure in liquid jet. Once again, sigma is the surface tension, D is the diameter of the liquid jet. So three cases I have discussed. The first case, in case of water droplet, the change in pressure is 4 sigma by D. In case of soap bubble, it is 8 sigma by D, and in case of liquid jet, it is 2 sigma by D. So let us take the first problem. The surface tension in a soap bubble of 50 mm diameter with its inside pressure being 2.5 Newton per meter square above the atmospheric pressure is how much? So here, in case of soap bubble, diameter is 50 mm, inside pressure is 2.5 Newton per meter square, and above atmospheric pressure, so PO can be taken as 0. And in case of soap bubble, so in case of soap bubble, we have seen that delta P is equal to 8 sigma divided by D. So delta P can be written as delta P is equal to 8 sigma divided by D. So delta P is 2.5 minus 0, so 2.5 is equal to 8 into sigma divided by diameter is 50 mm. So 50 into 10 to the power minus 3. So sigma is equal to 50 into 2.5 into 10 to the power minus 3 divided by 8. So the surface tension value will be 50 into 2.5 into 10 to the power minus 3 divided by 8. So it is 0.0156 Newton per meter is the surface tension. So if I see the option, so B option is correct. And this question is asked in engineering services exam 2015. Let us take the another problem. In order that a droplet of water at 20 degrees centigrade, surface tension is given 0.0728 Newton per meter, has an internal pressure is 1 kilopascal, greater than that outside pressure. Its diameter should be nearly. So we can write once again, in case of water droplet, this is the water droplet, inside pressure, outside pressure. If I cut, so it will look like that. This is the bursting force and the resisting force. Bursting force and resisting force or surface tensor force. So bursting force or pressure force is equal to the resisting force or surface tension force. So what will be the bursting force in case of water droplet? So delta P into pi by 4 d square is equal to resisting force is sigma into pi into d. So here delta P is equal to 4 sigma by d. So we can compute the what we have to find diameter. So diameter can be written as diameter is equal to 4 sigma divided by delta P. So 4 into sigma, the value of sigma is 0.0728, 0.0728 divided by pressure. So pressure is how much? It is 1 kilopascal. So 1 into 10 to the power 3. So 1 into 10 to the power 3 Newton per meter square. So the diameter will be 4 into 0.0728 divided by 1 into 10 to the power 3. So it is coming 0.29 into 10 to the power minus 3. So it will be diameter is approximately 0.3 mm. So B option is correct. So in the next class, I will discuss the what is capillarity and the expression of capillary rise and expression of capillary fall. So take care of your health and happy learning.